Hi everybody. So I have to admit, I'm actually a pretty boring kind of guy because instead of thinking about things that I should think about, you know, cars, football and girls, I tend to spend a lot of time thinking about systems, particularly systems of generating electrical power. Now, I have a view of things where I'm looking for stuff that is in common. So I can build a structure, a framework to hang that understanding of systems on. And the systems of the generating of electrical power are surprisingly simple. There's actually only three components. One component is the input. Then there's the output, which in our case is electrical energy, and then there's some way of matching one to the other. Now that all seems a bit woolly, so I'm going to give some practical examples, but the same applies across the board. So for example, with input. With input, we can only really input mechanical energy of certain types. You might do it with your arm, for instance. You might do it with the wind. You might do it with the water. However you do it, each has its own peculiarities. For example, I can only turn something at about 60 RPM because that's how fast I can move my arm, irrespective of the strength of it. Wind tends to be light and fast. Water tends to be slow and heavy. It's all got its own peculiarities, and those peculiarities of input are what the input device is designed to capture. Now the output device universally is a generator, of which there aren't that many kinds, because the only real way of generating electricity in our world is to wave a wire across a magnet, and it's pretty much how you go about doing that. Now if we want to match our input, say a water wheel or a wind turbine, to our electrical generator, we need something like gears, for example, in between. So those three components that I talked about can be represented pretty easily by a wind turbine, a gearbox and a generator. They're the three sections of a system for converting one form of energy into another form of energy, in our case electrical energy. Now it's all a bit esoteric, so my plan is to look at a specific example, actually a folding wind turbine, follow that through, showing how we might develop each of those elements. So let's make a start on this with the generator section. So what I've got here is a DC electrical motor, because electrically motors and generators are identical. In a motor you put power in, it turns. In a generator you turn it and power comes out. They're identical in their makeup, and all they are is a magnetic field and a wire that can move through that magnetic field. Now you can do it like this, where you rotate it, or you can literally waggle it up and down like a linear generator. You can create that magnetic field using permanent magnets like this one, or you can use electromagnets. It doesn't matter as long as the magnetic field is there. There must be movement between the two, so sometimes you rotate the magnetic field and sometimes you rotate the wire, but relatively speaking you are waggling a wire in a magnetic field. There's only two components to it, the wire and the magnetic field, and of course that leads to great debate, because to cram as much wire as you can in there you've got to fold it up, and people argue about how you fold it. There's also a magnetic field, and people argue about what's the best way to make that magnetic field, and there are various merits of each system that they come up with, but the essence is you must move a wire through a magnetic field if you want to generate, and there are just lots of ways of doing that that people get quite passionate about. So with the aid of this and a bit of string, me and Luke are going to show you something. Have a look at this. Pull! Okay, so that was a physics experiment to show what happens in a generator. And of course, physics deals with fundamental forces. It's actually all really very basic, very simple, and a bit dull until you come to apply it. But when you get hold of those ideas and apply those ideas, the whole world makes sense. But like I say, the problem is it's pretty dull to watch because it's so basic and so straightforward. In fact, it's so boring and dull that when you're explaining physics concepts, people like Brian Cox have to resort to images of spinning galaxies just to make it interesting. What you saw were vectors in operation, because in physics there are two kinds of quantities. There are scalar quantities and there are vector quantities, and vectors always have movement or direction, and very, very often both. What me and Luke did was apply two forces on some bits of string, and they had direction, which means they were vectors, and by applying those vectors to that weight, the weight moved. And the weight moved in a completely different direction at an angle to the two vectors that Luke and I were applying. Exactly the same thing happens with a wire in a magnetic field. And a magnetic field is a vector with a direction. When we move it, it's a vector with a direction, and it gives rise to a current, which is a vector with a direction. So I don't mean it's similar, I mean it's exactly the same as pulling the weight on the floor. You apply two forces at 90 degrees, you will get a resultant vector at an angle to the two forces that have been applied. This is exactly where Fleming's right-hand rule comes from. It's a description of what would happen with those vectors if you set them at 90 degrees to each other. We've got a magnetic field going that way, we move the wire that way, well the current's going to go that way, and that's all it does. It's describing how those vectors would interact at 90 degrees to each other. Those of you who are thinking about this might be asking the smart question, because in the experiment that Luke and I did, it was pretty simple. But the questions you should be asking are things like, well, what about if you change the amount of force you applied? What about if you change the angle at which you applied that force? And guess what? It would change the outcome, of course. And the same is true of generators, but generators are a much simpler system than the one Luke and I used, because we had friction, we also had gravity, then we had the two forces that we were applying. In a generator, you've only really got motion, field, and current. And of course the current can only flow in and out of the wire, it's going nowhere else. So there's only two things you can really change, and that is the angle that you attack this at, the speed that you actually move it at, and the strength of the magnetic field that you apply. So it's a much simpler system, but different things happen when you change some of those factors. Of course, what we're really interested in when it comes to generators is how much can we get out of it. We want to get as much as possible by playing with those factors. Now, changing the speed is pretty obvious, and we do that quite a lot. Changing the amount of wire that goes in there is pretty obvious as well, and you want to cram in as much as you can. Changing the strength of the magnetic field, well, use strong magnets. Problem with that is they tend to be a bit more expensive. One of the things that people get a little confused about and doesn't get that much attention is that idea of the angle that you actually do these things at. Because, imagine that's our magnet, imagine that's our wire. If the magnetic field is coming out towards you and I move that magnet that way, according to our Fleming's rule, the current will come out that way. If I move it like that, then nothing will happen. The reason nothing happens is just like the weight on the floor. That weight was free to move. If we stopped it being able to move towards me, doesn't matter how hard I pull, it's going to move towards Luke because it's got a constraint on it, and the same is with the wire. So if I'm doing that with it, nothing's going to come out because it can't. If I do that with it, then something's going to come out. So the angle that the wire makes to the magnetic field as it flows will affect the amount of current that comes out of that wire. So that's going to be the best, that's going to be the worst, and that's going to give you less than that, but more than that. So the angle really, really matters. So here's a circuit. So to make this coil, I've got this massive coil of hair-thin wire, a bit of a wooden board, and two bolts with some rubber over them. And what we do is put the bolts in the board and just wind the coil round and round, and then tape it all together. It'll make more sense when you see it, so let's get on with that. there's our coil wound. Now what we've got to do is jam it on this former. Incidentally, if you want 3 fares, make 3 of these, and then we just wind that onto the former in a serpentine. And when you've done that, that is what you get. Now, on a practical point, you might notice on the coil, I put these little tape bits here to hold the coil together, and in that position, because it makes it a piece of cake, to then put the coil onto the actual former. Let's analyse it in terms of those angles we've just been talking about and how it's going to affect generation. Now, because it's a circle, of course, it's narrower here than it is here, because it's a circle. This section here is going at the wrong angle. It's at 90 degrees to the field, so that section's going to generate nothing, as is that section. Now, because we've wound it this way, we've had to put this at an angle in order to get from one point to the other point, and of course, that being angled means it's going to generate less than if it was straight. So if we want to improve this, then we need to make this as short as possible, and we need to put this as straight as possible, and we'll get the most out of this kind of serpentine coil. So what do? Well, we can twist the serpent around, and if we do that, we get this. I designed this in Tinkercad, and as you can see, all I've done is turn that serpent around 90 degrees. So instead of running like that, it runs up and down. Now, the Tinkercad files are available. I've put them up there and you're quite welcome to download them, but you can see if I wind the serpentine coil, then because it's no longer going in a circle that way, then there's less wire at 90 degrees. I mean, we need the wire at 90 degrees because we have to join them up, but there's far less there. And because they're now going equally, they're going to go much straighter. So this is going to be a huge improvement on this. So to put this together, I used this. It's a thrust bearing. The outside diameter is 35mm, the inside diameter is 22mm, and it's 10mm thick, and I just bought it from Amazon. Then I printed 2 parts, the housing and the rotor. In the housing, there's a thrust bearing there in the printed recess. And then we have the race there, and I've got an 8mm bar going out to the height of this. That completes that bit apart from the coil. The rotor, which is the second bit that you're going to print, again, you've got the other side of the thrust bearing in the recess, 22mm bearing, so that it can sit on that bit of bar. And then around the edge in a north-south, I've got these, which are N35 neodymium magnets, 10mm by 2mm. They go in there, and that finishes the rotor, so the rotor sits nicely in there like that. The only thing we've got to do then is put our twisted serpent around there. To make that, here we go, it's just one big coil, and I've done a number of videos on how I make these. I just wind the coil, and then there's bits of tape holding the coil together, and those bits of tape match up with those sections there. So I've got to bend this into shape, and to bend it into shape, so a piece of cake, you just do that with it, matching the 2 bits of tape with each other. You do that all the way around, and then we can bang that onto our stator. Okay, quick and dirty test, LED. Now, an interesting point is this is not only easier to do than a standard coil. We've got so many standard coils to make, there's 36 of them. But because it's a serpent, then the bit that would be in a standard coil going across the top, well, it isn't there. And because it isn't there, it isn't wasted wire. That makes it more power dense than if you bothered to wind separate coils. So these serpent coils have a lot going for them. Anyway, let's give it a spin. That's pretty cool. Of course, we've got to get a voltage out of this. Okay, we did that by hand, got a few volts out of it. I've wrapped a pull cord around it, and we'll see what we get.
45 volts! Whoa!
45?
Yeah.
Look at the balance on. Well, that's a bit awesome. This could spin for ages, huh? Wow. That's just on that bearing. Now, when you're thinking about coils, you're really thinking about Fleming's right-hand generator rule, where the movement, current and field of magnets are set at 390 degrees from each other. So when you have movement in one direction and you have a field crossing other, the direction of the current is always going to be given for you and fixed. Of course, in a generator, the movement's the same way, but the field is going north-south, north-south, so the field is exchanging. So what we effectively want to do is have the current move one way and then the other way. We want to join that up somehow so that the net effect is the current moves only one way. Now we can do that really simply. Actually, we just do that like this. You'll notice that the wire goes up one side and down the other side, and so the current moves in the right direction. And a serpentine coil represents that. If we can keep these wires in this direction, then we've made it more efficient, because the wires are at their most efficient orientation, and that's what matters about the serpentine coil. Now, in order to get that to do that, of course, we want the greatest amount of wire in a straight line going through our magnetic field. So the longer the magnetic field, the more of this wire will be straight and the more efficient it's going to be. Of course, we can do that really easily by using bigger magnets. So what I've got here are a bunch of 65mm by 1cm by 3mm N35 magnets, and I've drawn this up on Tinkercad. What this is 3 bits, and that's all we actually need. We need a rotor, we need a stator, and we need a bit act as a cover that can join it up to the rest of our wind turbine, which is exactly what we got here. We've got a stator, where I put some wire on already from video 1929. That's our rotor, which is where our magnets are going to go. And that's our cover. And all 3 just slot together like that to make our generator. So our generator is actually pretty simple to make. The magnets go in a north-south, north-south orientation. And here they are. Here's our N35s. So we do them north, south, north, south, north, south. We put our serpentine coils onto our stator, and one's already been put on, courtesy of video 1929. There are 200 turns on here, and I've got 2 more to add. Now, I could make this 3-phase by putting the coils at 120-degree separation, but I'm actually just going to line them up with the slots that I've got ready for them. So, let's put those on. There is my rotor. Now these magnets are north-south, north-south, and there's 12 of them, and both of that's important because there are 12 of these wires here. Of course, we've got 6 on the crown and 6 on the bottom where it makes the turn, and that matters because as that goes past there, it'll generate going past the north, and that will force the electricity to go in that direction. Now, if it was north and this one was passing a north as well, then it would both go in the same way and we get nothing out. Because we're making this one pass south, as this one passes north, then that goes that way and then that way, and we can get what we want out of it. So we have the same number of straight bits of wire as we have of magnets. The magnets are in north-south, and then these crowns and dips, it doesn't really matter as long as you've got 6 crowns, 6 dips to make that crown. And those are the keys to a serpentine coil. Now the coil itself, if you haven't watched 1929, is super easy to make. And that's one of the other joys of it, is how easy they're to make. Because to wind 12 coils as individual coils and then lose half of that copper is a little bit depressing and takes forever. To wind one serpentine coil takes no time at all, and you don't need half of the copper. So we've put it on to there, and we've got our rotor, and obviously our rotor goes in there with a spacer of an 8mm washer to make sure that it spins freely. Now all we have to do is pop our cover on, give it a spin, and it'll generate. And we have 6 exit wires, so we need to rectify what's coming out of there, put it under load, and give it a test. To do that, I've got this massive chunky cog that I'm going to put onto there. So I'm going to put that on there and put rectifiers on there. Okay, that's it. I mean, you can have choices here, eh? One way, which is the way I've chosen to do, is take each individual coil and rectify it using this rectification circuit. The other way is to take all of the coils together and rectify it as 3-phase using this rectification circuit. Now, I've done each coil separately because, to be brutally honest, I don't quite know what I'm going to do with this, I know what I'm going to do with it. I'm going to stick it in a wind turbine. What I mean is electrically what I'm going to do with it. Because on here I've got all my positives coming out from that rectification circuit I showed you, and on here I've got my negatives. So I've rectified each coil individually to give me 3 positives and 3 negatives. You don't need to do that. You can do it as all 3 coils rectified in a 3-phase rectifier circuit to get 1 positive and 1 negative. The reason I've done it like this is because if I join those up in parallel, I'll add the amps. If I join them up in series, what I'll do is add the volts. So I could join my positive to negative, and take my positive and negative out here, and they will be in series. Or I can take all of the positives out, all of the negatives out, and they'll be in parallel. It just depends what I want to actually power with it. Now I'm going to connect this up in series, and we're going to give it a spin with an LED. This LED takes about 20 volts or so to turn on. Okay, so here's my positive, and we can stick it onto the positive like that. Now obviously the negative comes out of the other side, and we can take the negative to the other side positive. Then we take that negative to the other side positive, and then we take our negative out. So what we've done is connected this in series. So that's now connected in series, and the voltage output of all the coils will add together, and it'll be some crazy voltage. So let's give it a spin. I've got the meter here. We'll see what kind of voltage we get out of it. What we getting, Luke?
Oh, 28.
28?
29, 31.
There you go. So we get some super voltage out of it just by spinning it. Now this has a turn on voltage of around about 20-25 volts. So instead of connecting it to the meter, we connect it to our LED. We should be able to get that LED to light, and so we're getting real power out because it's doing some work. And there you go, lighting an LED. So that deals with the first part of the system, that is a generator. Now remember, a generator doesn't actually generate. A generator converts mechanical energy into electrical energy. It has its own specifications. The one we built needs to spin quickly, so we need it with a high RPM. Of course, to do that, we're going to take an input, and in our case, our input is going to be from the wind. That wind needs to be converted into high RPM. Now, because we haven't put any metal in this, it's got a very low torque, so we need high RPM and low torque, and that means gears. And your own flour? I've done it on a quernstone. A quernstone's just a flat piece of stone with another stone. You put the grain on, you rub it backwards and forwards, and it is back-breaking. Of course, the next development was to make it turn in a circle, but it was still hard work, and it's where the phrase, the daily grind, comes from. You were grinding your own flour. So when you're looking at a way of escaping that drudgery, what you want is power. You imagine how back-breaking using that quern would be, but here at Crabblecorn Mill, they've got 10 stones in 5 pairs, each weighing a ton, so there's 10 tons of stone right here, and they could process 40 tons per annum of grain, and it's no surprise. Here in the hopper, they've got 60 kilos of grain. This is the horse that holds everything. It's a damsel and a shoe feeding it into those stones. Those stones are turned by the river, producing the flour. Good things about water, there's a lot of it, and it's heavy, so there's a lot of force, but it's slow. So if we want to use that power to do something like grind flour, then we need some way of capturing it, some way of moving it, some way of changing its direction, some way of applying it, and some way of changing the speed and torque. So we need to do basically 5 things. The way we do those things is through gears. Nobody really knows who invented gears or how old gears are. There are records to the 4th century BC in China, and of course the Antikythera was discovered in the Mediterranean, and that dates back to 150 BC with a history through to Alexandria, and you're talking about 3rd century BC. better place to show that is somewhere like this. This is Crabblecorn Mill in Dover. It was first built in 1812. It's a fantastic demonstration of mechanisms and gears. This is the main wheel. 2 people died in here. The water wheel captures the power, the stones apply the power, the rest of it is the mechanism of the gears, and they're the same yesterday as they are today as they will be tomorrow. And it's arguable that the windmill, watermill and clocks represented the height of medieval technology when it comes to gearing. And in a watermill you can see those 3 functions clearly, and those 3 functions are transmission, force and rotation direction. What we mean by transmission is speed. Different sized gears can be used to efficiently change the speed of a system. Large gears with lots of teeth, when they interlock with small gears with few teeth, have to spin fewer times to keep up with the total motion of the machine. The smaller gears have to spin faster, and this gives you a way to increase rotational speed. Force is in a similar setup. You can use gears to increase the force of a system. That extra force doesn't appear out of nowhere. Turning the small gear fast will make the large gear turn slower, but with much more force. This is what we mean when we say that torque is traded off against speed in gearing systems. The final one is rotational direction. Gears are very useful changing the direction of the rotational motion. Spur gears, for instance, can reverse the direction. Worm gears change rotation by 90 degrees, and bevel gears can transmit motion around corners. Milling flour is perhaps the most well-known application of a watermill, but they were no means restricted to just that. They were used for trip hammers, for things like forges and paper making. They were used for bellows, again for forging and forcing air, and they were used for sawing in lumber. They had the same principle. You had a power source, the water. You had an application, bellows, trip hammer, saw, grinding, and you had some method of communicating the two in an appropriate way, which was the gearing system. This is the same problem we have today for power generation, and the same principles apply. We have some kind of primary input power. Water, wave, wind, arm strength, cycle power, whatever it is. There's some kind of input. Then we use some kind of gear mechanism to change it to what's appropriate to the output. Now, when you're generating power, what's appropriate to the output is being able to spin a generator at the rated speed and rated torque. That's what you're looking for when it comes to putting gears between those two elements. But in essence, you're doing exactly the same thing that the forefathers did when they were sawing logs, hammering steel, grinding grain. We got this. We basically tore the heart out of a PC fan to get us what is effectively a generator. Now, it's a bit weedy and wimpy because it's got very little copper in there and a particularly weak magnetic field, but it works and we can get a surprising voltage out of it by spinning it by hand. Now, there's next to no torque on this, and if we remember that a generator generates voltage in direct relationship to BLV sine theta, where B is the strength of magnetic field, L is the length of the wire, sine theta is the angle the wire makes the magnetic field, and V is the velocity or the speed at which it turns. When we have a fixed generator like this, and the only thing we can vary on that is the speed or the torque, and of course they play off against each other. And this one, next to no torque. It was a fan motor, so we know that we need a lot of speed. And one way to get speed is to add gears. Now, there's a ton of different gears you can use, and they all have their pros and cons. So we could do magnetic gearing. Now, that does have a tendency to slip, but it's a nice gearing system. We could use straightforward gears and just build up the gears, but they would be quite large. One of my favourites is this. It's a planetary gear system. This is called the ring gear. Then we have the sun gear. And then we have the planet gears, these little one, and this is the planetary carrier. Now, the gear ratios of these depend on their relationship to each other. So if we count the number of teeth in there, count the number of teeth in there, add them together, we'll get the effective number of teeth on the planets. That always means that the planet is the biggest number of teeth. The sun is always the smallest, and the planets are always the greatest. The gear ratio of the sun to the planets is always the biggest gear ratio. In this particular one, then we have a gear ratio of 3. So every time I turn that one, the sun will turn 3 times. Now that's kind of cool because it means that if I put that on there and I give that 1 turn, I'll get 3 equivalent turns out of that. And that's what we're looking for in something like this, because the more speed, the higher the voltage. Of course, it's not terribly useful like that. So what I've done is I've printed out a sun gear. There we go, like that, because this will fit nicely into there to make us, there we go, something we can drive easily. And of course, to do that, I turned to Tinkercad and I developed this whole thing in Tinkercad. If you have a look at it, you can see with the 3 legs is the sun gear. The smaller ones are the planet gears, and then we have stacking ring gears where we can stack these one upon the other. So if we print all of those off and connect them together like this, then we can put that in there and we put the ring on over it like that. Then every time, if we hold the ring still, every time we turn that sun, this will turn 3 times, because that's not very much, but we can stack them. So if we stack another one on, then we'll get 3 times 3, 9 times. Stack another one on, 27 times, and we can keep on building up a compound sun and planet gear system until we get that to spin until we can't turn it anymore. Now we can have a look and see what we're actually getting. So let's do that. Right, I've got a ring gear right there, and at the bottom we've got the PC fan motor with its cog on it, and I've connected it up to this meter. And if I give that a spin, we'll be able to generate a voltage. Not a great deal, about 0.5 of a volt or something like that. Now that gear operates as a sun, and of course what it needs is some planets. And I've got here a sun gear where the planet carrier is integral to the sun gear and the planets are attached to it because I can stack them up. If I put that on there we go, we now get a sun and planet arrangement, and if I spin that, we get a much higher voltage. And I can keep doing that by adding rings and adding these sun and planet arrangements to build up a compound arrangement where it adds on. So what we get with one of them, there we get normal speed, put 1 on, it's 3 times the speed. 2 on, 9 times the speed, 3 times 3. 3 on, 27 times the speed, and so on as we add these up. Okay, let's put a few on and give it a go. So I've got 3 sections, so 3, 9, 27. We're going to give it a spin, see what kind of voltage we get. Madness! Okay, that went well, so I've put another layer on. Let's see what we get. We did pretty well getting 17 volts out of this tiny little motor, and the point of all of this, well, it's exactly what I was talking about when we were at the mill. There's always a mismatch between what you're trying to input and what you're trying to output. When it comes to wind turbines, you've got a wind turbine that is capturing the wind and turning, usually quite slowly with quite a lot of torque. You want to be able to turn that into quite a lot of speed. Torque requirement on this is so low, what we need to do now is gear it up. This is the connection ring, it fits on the generator, and then our gears can fit on that. Now originally when we looked at this, this is what we came up with. We integrated the planets with the sun gear so that we could make it stackable, drive them, and add that multiplicative factor for these planetary gear systems. But I thought that was a bit clumsy. It was just me looking at it to begin with, so I redesigned it into this. This is what you're going to see in those Tinkercad files. And what it is the planet carrier is now a ring with 3 prongs on it. The planets go on there, And then the sun gear is integrated with the fixing plate, and that whole thing just glues in. Now this is all plastic because we're wanting to test it. If you want to make this stronger, you'd replace those pinions with metal and maybe put bearings around the planets. You'll see that there's a bearing right in the center of the sun there. That's to help it spin freely along an axle. So now we can get a number of these, stack them up, and we get the same stacking gearing system that it had before. The ratio of each one of these is 3:1. So if I put that on there, it's 3:1. If I put that on there, it multiplies, it's 9:1. If I put another one on, it's 27:1. And we have this hole going right the way through the center. And that's so we can do that with it. The whole stacking planet gear system is held in place by a bolt with a nut on it, and the bolt fits in the little hex at the bottom there. They all spin independently and freely of each other, courtesy of that bearing that we just put in. The bearing's a skater bearing, 22mm by 7mm by 8mm centre. The other thing we've got is the actual ring gear itself. Again, these are available in that file. Now I've done this for 3 of them, and those 3 just slot in there like that. Now if I turn that, I'll get 27 times the output. And that goes on there like that. There we go. That's our gears. That's it. Now I put a stand on it and I put a handle on it. The handle just detaches actually, so that we can hand crank it. But of course, what we're aiming for, if you remember this, our folding wind turbine. So the folding wind turbine will actually go on there like that. What I need to do is make an adapter between this and the wind turbine blades, and then we're ready to rock and roll. So we're nearly there. But I put this gearbox on, and it is a 27:1 planetary gearbox stacked, as we saw. What we're going to do is read the voltage out of it by me hand cranking it, and we'll see what we get out of it. Now I have connected it up in series at the back here, and you can see the series connection. Again, it's like this because I still haven't decided how I'm going to connect this. But if we crank this handle, we should definitely get some kind of voltage reading out of this. Let's have a go and see. You get 104 volts out of that. I'm a bit scared about taking it any higher because, you know, I'm a bit scared I'm going to burn the wires out. But there you go. 104 volts out of cranking it by hand. So maybe I could put another stage on there. But I'm not sure if I'm going to do that or not, because that's actually pretty. So in this system, we've now got to the bit that perhaps has most focus, and I'm guessing that's because it's the bit you can see, and that's the bit where we input the energy, the bit where we capture the wind and turn it into rotation. And like lots of things, if there's 2 opinions, you'll find 2 camps arguing viciously against each other about which is best. But it's not really relevant here, because we're looking at a system, and the thing that we choose as the input is only really an example of that. Now I was looking at foldable portable wind turbines, and I was astonished by 2 things. 1, how expensive they were, and 2, how pants their output was. It was like very low for a huge overpriced piece of kit that I thought, over this whole video project, if we ended up making a portable wind turbine, that'd be really cool to do. So I've chosen that only for those reasons. But the wind turbine bit itself just represents the input of the system that we're talking about. Because we're talking about the input, the output, and the link between the 2. The input, it really doesn't matter. It could be your arm, it could be a water wheel, it could be a folding turbine, it could be a VAWT, it could be HAWT. Whatever you think is the best, this is the same way that you construct absolutely everything within this field that we're talking about. So I've chosen a folding wind turbine design for that reason. The way they make them portable is essentially to fold up the blades. If you can fold up the blades, you can have yourself a portable wind turbine. I made the blades, there we go, out of pipe. This is just ordinary soil pipe. I did this before, and here is how I made them. In order to make the blades, all we're going to use is a bit of this. This is a 100mm diameter or 4-inch. This particular one is drainage pipe, you can tell by the colour. If you get the black one, that's soil pipe. It's a bit difficult to see your markings on the black, which is why we're using this one. but either will do. It's about 5mm thick, it's good stiff plastic, and we can make this into 4 blades. Now the blade length is going to be 50cm long, so what we need to do is cut off a 60cm section and then divide that into 4 by marking it in quadrants and sawing those quadrants up. So that's what we're going to do. For wind turbine blades, really easy to make, I think pretty cool. These are 53cm long, so we're going to have a wind turbine with a swept area of 1 metre. Then we've got this, which is this 3-part, and 3 of these that slot in there, because they'll close up that way, open up that way, and that makes it foldable. So in order to make this, you need to, print off 3 of those, 1 of those, and we've got a bit of steel, a steel bar there, which is 100mm long, and some 35mm long steel bars, 3 of them. What we do is we take these sections and put them in there, and put our steel pins through that section there, so that they can swivel. Then we glue our blades onto there, so that they're oriented like that, with the long blade side going up the highest. We'll put those on. So when you've glued those on and you put the pins in, that's what you get. It is a folding turbine blade. It's 1 metre across and it weighs a few 100 grams. So it's pretty compact when we fold it back up. Now you would have also noticed that we had this, and this, and this, and this in that file. This is to make a magnetic gearbox that we made in video 1922. But essentially in there is enough space to stuff some M8 nuts, and that's what's in there, 8 of them. We've stuffed 8 M8 nuts in there. That's a bit of 8mm bar that's shoved in so that it's the same level as that. And then we've got this section here where I've put 2 skater bearings, one here and one here, and they're just standard skater bearings. Now that one, you put a washer on it like that. It goes through the skater bearings like that. We put another washer on there, and then we stuff that into there like that. When we've done, that's what we get. Now obviously these blades are going to keep folding shut, so this bit is a nose cone, and it goes on the projecting bit of steel right there. There we go. And that stops the blades folding back shut on themselves. When you want to close it, you take that off and those blades can fold up. We have a folding wind turbine. And this is the gearbox. Remember, it's video 1922 because it's a magnetic gearbox. We've got our 8 nuts in there. Around the outside here, we've got 12 spaces to take neodymium magnets. The stronger the magnet, the better, but we can use N35s up to N52s. And they are 15mm diameter circular magnets, 4mm thick, and they go in there north, south, north, south, north, south. On this section, which is the final drive section, it's got a bearing on it. It goes on the other side of the steel like that. There we go. That's free to spin. when we put the magnets in there, and there's 4 of them at 15 millimeters diameter circular magnets, 35 to 52, 4 millimeters thick, they go in north, south, and that creates our magnetic gearbox. Now when we open that up, that incidentally is to stick on a broom handle, put on our nose cone, we have a collapsible wind turbine. Now this section here, I've done it so it takes a bike dynamo. So the bike dynamo goes in there like that. And if I hold that up, I'm going to get somewhere between 3 and 5 watts out of that. But let's put those magnets in and then take it out and open it up, see what it does in the wind. Put it together, we're outside, we're going to try it in a bit of wind. And guess what? I've run into a couple of mates of mine.
I'm Ginger Jack. Hello.
And I'm Jacob.
Okay, so Ginger Jack and Jacob are just going to give us a hand to test this and see if it works. It's on a broom handle. We're going to stick it in the air and see if we can get it to spin. That is look at that.
God, that's proper.
Wow. That's amazing. Look at that go. That's awesome. I have made a modification to this head here, and what I've done is on the reverse side I've mirrored the gears. So this sun gear now fits in there, and of course that becomes the drive. We can't put it straight in there because we need to put it onto here, and if we just put it straight on there, the whole thing would come out. So there's a cap that goes on there to hold everything in, and of course that cap needs to be on first. So that cap goes there, that goes in there, and that's how we connect all of this stuff. And then we stack up our 3 gear system so that we can then slide it into the gearbox housing. I have of course prepared these in Tinkercad. So if anybody wants those STL files, the link is in the description. They're freely available to anybody, and any improvements or changes you want to make to it, please feel free. Now all we're really going to do is connect all these together in that stack of 3 that we did before. So it makes a stack of 3 like that. That section goes on here, the whole thing slides in there, and that cap will be in between to fit onto there. So we're going to put that together. There it is fitted together. We've got a bolt sticking out there, so we've got a pretty nose cone. Again, it's in the Tinkercad files, and that just press fits onto there. Okay. And then they're free to flap up and down, and now we can slot the entire gearbox back into the wind generator section. And when we've done that, there you go, one folding wind turbine. That's pretty wicked actually. So it folds up really nicely. That's a part of it. It's a bit heavier than the other one that we were looking for. We've got about 2 kilos here now, but I've left a foot on it right there. That foot plate obviously is going to take a pole or whatever you want to fix it. You'll have to make a fixing so the foot plate can fit to whatever it is you want to fix it to. And then of course this back piece for an actual wind turbine, we need to put a pole coming out of the back here with the fin on it so that it's wind direction. But that is the wind turbine, the folding wind turbine, pretty much finished. Now there is one other issue with this that I want to discuss with you, and that is the blades. The blades obviously fold out. They're going to collapse back in unless we do something right here. And that I have been pondering long and hard, and the solution I've come up with is clips. Just put a couple of clips on there, they snap into place and they hold it out. So they hold the wind turbine blade out. I think a better solution is required. Something like maybe a retaining pin or some other way. But I'm going to use these clips to hold it out because it's expedient and quick, and that's what I want to do because I want to get this thing tested. That is how to go around building any generation system. Doesn't matter. I only chose the folding wind turbine as an example because all the way along the way, you're going to be making choices. If you understand that the system is made of 3 basic components, input, output and link, you're going to be able to go a lot further, because a lot of those choices aren't a question of what's best. They're actually a question of what's appropriate. I mean, if you live in a built-up urban area, you are not going to be building a 5-meter wind tower. Equally, if you're going backpacking, you're not going to be lugging a 2-meter VAWT with you. It very much depends what you want to what's going to be appropriate, rather than what is best. Best must include your situation, your skills, your money you've got available, what objectives you have for it, and having choices for that is really important. But being able to put those together in a logic so that you can actually build something within a framework, I think is equally important. Now, like everybody, I have my favorites. I mean, I'm a particular fan of the serpentine coil for the generator, which is why we went into it. I'm quite a fan of compound gears and magnetic gears, although we ended up with planetary gears. And I'm a huge fan of VAWTs, although we did a foldable HAWT. So it's not really a question of best. Best is just such a broad concept, which is why there are so many different types that can become confusing. But the whole system itself, it's always the same 3 things. Anyway, I hope you enjoyed the video. Thank you very much for watching, and please do remember to like and subscribe.